continue with this keynote panel that we have titled Today's Deployment in Tomorrow's Tech and AI Data Center Batteries. And I have the pleasure of hosting this panel with Tiffany Wang from S&P Global, Katherine from TDK Ventures, Chinmay Morankar from WSP, and Sam Arons from Beale Infrastructure. I will give the panelists a chance to introduce themselves, but I just want to give a very brief intro about this panel. It's become abundantly clear today that power, not capital, is the bottleneck of the AI build-out. And an analysis by Currents, which was formerly known as Sightline, showed that roughly half of US announced capacity will never get built. The implications, massive backup power systems are becoming table stakes for data centers. This is clear with Google's 4.7 billion acquisition of Intersect Power's 10.8 gigawatts of pipeline solar and storage, and Amazon's 83 million purchase of 1.2 gigawatts show that hyperscalers are now willing to directly get involved with power project management and development if it lets them bring more capacity sooner. Before I give a chance for the panelists to introduce themselves, I want to ask Tiffany, who's at S&P Global, about just a question to set the stage for the rest of this discussion. Tiffany, good to have you on. Could you please share with the audience broadly the use cases of BESS in batteries and data centers?
Sure, and thanks for having me, Michael. So just to kind of set the stage, like you said, here at S&P, we've mapped out 5 key use cases that we see that BESS is being used for data centers. The first one is BESS being used increasingly in PPAs. Data centers are now signing hybrid renewables and BESS PPAs to secure long-term, low-cost electricity and meet their sustainability goals. This is kind of a newer development, as historically PPAs have largely been solar or wind only. Another use case that we're seeing emerging is BESS for flexibility. So that means installing on-site behind-the-meter BESS to reduce your required peak firm capacity and to speed up your interconnection timeline. Backup is another use case where you use BESS to essentially replace or reduce reliance on diesel gensets for backup purposes. And then power quality as well. So using BESS to smooth power quality issues caused by rapid GPU load swings during AI training. And last but not least, gas optimization. So using BESS to optimize your gas generation on site, helping to reduce the sizing and amount of wear and tear that you have to do, that you typically have to do for your gas gen. So yeah, it's a combination of some of these use cases that typically is kind of driving BESS installations for data centers right now.
Perfect. And we have this power infrastructure problem with data centers. And I want to give a chance for everyone to introduce themselves with this question. We're doing this thing a little bit differently than we typically do. So my question to all the panelists, and when you give your answer, please introduce yourself, where you work, your role in that company, and then your answer. If we separate the problem that we're currently facing into a couple of buckets: energy availability, power quality, reliability, and speed to power, where do you think batteries are creating the most value today? Um, let's start, Tiffany, since you just went, let's start with you, and then we can go to Sam next.
Sure. So in terms of what data centers value most, currently, obviously, speed to power would be the top consideration. So I would say the use case that I think that BESS is appearing in the most would probably be for flexibility, just basically helping to reduce your peak firm capacity and to help speed your interconnection to the grid. Oh, and to introduce myself, my name's Tiffany. I am a renewables analyst at S&P Global, and typically I focus on issues regarding pricing, supply chain topics, specific research on like topics like BESS for data centers. And yeah, I'm happy to share basically key findings from a report that my colleagues and I recently wrote called Best for Data Centers. So happy to be here today.
Perfect. Thank you, Tiffany. Sam, um, your intro, and then also, what will be the most valuable thing for batteries?
Morning, everybody. Sam Arons here, VP of Energy and Sustainability at Beale Infrastructure. First time caller. Good to see you all. I lead our utility contracting and energy work at Beale. We're a third-party data center developer based in San Francisco with offices in a couple locations around the country. We build hyperscale data centers and lease them to hyperscalers, not surprisingly. When it comes to the most important use case for BESS, I would say speed to power, definitely. And that can be achieved through, I think, a number of the kind of 5 pillars that Tiffany laid out. And yeah, look forward to the discussion today.
Fantastic. Thank you. Next, we have Katherine.
Hi everyone, my name is Katherine. I'm an investor at TDK Ventures. TDK Ventures, we are 500 million fund, investing a lot of early stage global deep tech startups. In the data center space, we already make a lot of investment in the energy infrastructure, including solid state transformers and also grid scale battery storage. We also made investment in the data center cooling and also more on the compute side. For this question, Michael, I think I will vote time to power as well, because right now data center they're in long queue lines, like up to 10 years to be interconnect to the grid. And also, I would also highlight the big value of batteries are providing the flexibility to the grid. Because if you look at the total grid capacity, we actually have enough capacity to serve all the data centers, but it's just not at the right time when you need it. So by adding the flexibility, you actually you don't need to upgrade any existing transmission lines. You don't need to make any new infrastructure build. You can directly, just by adding 0.5% of flexibility, you can already unlock 100 gigawatts of capacity from the grid. This is one research last year from Duke University. So these are all positioning batteries into a very favorable positions.
Yes, we'll definitely be discussing more of that availability later. A very hot topic. And then Chinmay, please.
Hey, hi everyone. Thanks for the opportunity to come here and be part of this panel. First time caller as well, Sam. So I lead the systems team of WSP USA, VP of Systems Engineering. My team is essentially made up of like mechanical and electrical engineers. And the easiest way to define what we do is like we are design and optimization team within the larger power and energy organization of WSP. And for people who don't know WSP, WSP is a engineering services firm, global. So most of our day to day is working with different microgrids, which includes a lot of these data centers and utility scale projects. So coming to your question, Michael, I think like the major value that BESS can provide or is providing right now, I think it's like power quality and reliability, especially with the operational behind the meter kind of like data centers that we are seeing. I agree with what Tiffany, Katherine, and Sam said as well. But I see the challenge with BESS is like essentially it's not a generation source. Like that's the primary limitation. You always have to think about like how it's gonna get charged and discharged. So like with the projects that I'm seeing, like I'm seeing most value for BESS coming out of like power quality and reliability.
Fantastic. So a little bit of a variation in answers here, but largely we see some key value propositions for BESS. I want to start off this panel into some individual questions. Katherine, in our conversation before starting this panel, we've argued that we should really start with the true constraints and challenge the assumptions that we have for this topic. So my question to you, what assumption about AI energy demand do you think deserves the most scrutiny today?
Yeah, I think for many other discussions in the data center topic, energy topic, I think I always hear people talking about we are overhyped on AI. There will be big bubbles on both AI compute. We actually are also overbuilding on the energy infrastructure, looking at all the nuclear, all the tech giant, Amazon, Google, they are starting to like investing in nuclear power plant. They are investing like long duration energy storage. So people are always arguing, like, especially in the future, we expect the token economy will become better and better because the compute efficiency will continue to improve. So the biggest underlying problem is that whether we are overbuilding the energy infrastructure. So I would love to hear other panelists' answers on this as well. But my personal thought is, I think we have to think about Jevons paradox. So when something becomes more and more available, becomes more and more cheap, for example, the token economics. So when we're getting more and more efficient, for example, we invest in Grok, which acquired by NVIDIA by $20 billion, we can reduce the compute power by to 1/10 using LPU, which is the new format of inference. So we all know the compute efficiency will become better and better, but at the end, I believe it will unlock more and more available. It will unlock more and more compute everywhere. It's no longer just being the giant centralized data center, but it will be like in your home, in your car. Like last week, I was in GM's Empower press release. They're talking about in the future, every car, every EV that you're driving is actually also bringing compute from cloud to the edge, where it is a unit of combined compute and energy. And also in your home as well, one of our portfolio company called Span, making home smart panel, they are partnering with NVIDIA to build your AI data center in your home. So this is what I believe that we have to really think about a future where you will unlock AI compute everywhere in every corner of the world. And then in that world, it will only end up drawing more and more power from the grid. So this is a kind of underlying topic that, especially for this group, a lot of battery professionals, I think this is something that worth discussion and to see where we are in the future position.
Absolutely. And if any of the panelists like to chime in at any point in the conversation, please feel free to be empowered to. Sam, I'd love to hear your input on Katherine's response here about overbuilding. I'm sure that overbuilding might be advantageous to Beale. I'm kind of curious to hear like where your assessment on that is.
Yeah, we're living in an interesting moment, obviously, and I was gonna my mind went to the Jevons paradox as well, Katherine, because I think you're absolutely right. There's sort of an insatiable appetite for compute, and the more efficient things get, the more we're going to use. I mean, we're already seeing limitations on token maxing, right, which now is kind of becoming a naughty word in some places because there just isn't enough compute and it's getting too expensive. So I think that there will be demand for it. On the other hand, if we look back to a kind of historical analogy of the fiber build out in the kind of 90s, 2000s timeframe, there was a period where there was a lot of overbuilding, sort of a frothy market at that time as well. And yes, there was kind of that, the 2008 financial crisis, and there was a period of time where that went unused, but then it also got snapped up quickly and kind of allowed the next generation of internet companies to flourish based upon this, gigantic amount of fiber capacity that existed at, bargain basement rates. So I think that while maybe there's some, risk that could happen with respect to energy build out or being overbuilt, I think that ultimately, whether it's through kind of Jevons paradox or, future growth in directions that we can't even conceive of right now, I think it will get used. But there might be some, there could be a period of uncertainty until we get there.
Absolutely. And in building these data centers to support compute, Sam, we had a conversation previously about the two teams at Beale, the land team and the energy team. And this is actually a dynamic that I was not aware of and would be super helpful for people to understand in this environment. Could you describe a little bit more about what these parties do at Beale and what the dynamic looks like?
Yeah, definitely. And I guess I should have said in my introduction, before Beale, I spent about 10 years at Google on the data center team there. So I can maybe speak a little bit to both companies, I guess. But But I think largely the structure is somewhat similar, which is that actually kind of the power team and the land team or kind of the development team in a lot of ways are two halves of the same team. But we kind of focus on different things and we work together to find sites that, can be built essentially. And in some cases, we bring sites to the table kind of from an energy first perspective to say, okay, this is the right RTO to be in because it has the right rules for data centers, the right rules for interconnecting load and generation, on faster timeframes. This is the right state due to the regulatory regime or a particular large load tariff that has been agreed upon, and it makes the utility contracting process easier or the IPP contracting process easier. In other cases, the land team is the one coming to the table to say, hey, we found this like huge parcel. We think that it's more likely to be able to be entitled and kind of get through the public approval process than some other locations, although, as I'm sure we'll get into, that's getting harder and harder everywhere, it seems. But either way, we on the energy team have to provide the input as to what the energy picture is and, explain what is the transmission situation, how fast do we think we can get stuff built? Is it going to be, X million or Y million to build all this stuff? What are the rates and all the rest of it? So it's an important, distinction between these two teams. And really, we work closely together, hand in hand, to make these projects come to life.
Perfect. And with site selection, what does the dynamic look like between these two teams?
Yeah, so I mean, I think, in some cases, we're getting pitched sites that have kind of gotten through some portion of development. In some cases, there are even sites that are fully entitled that have made it through the public approval process already, which is like an increasingly valuable thing these days. In other cases, it's just complete greenfield, farmland that has to go through a rezoning process with often city or county approvals that are needed. And that can be challenging, given the backlash that we're seeing these days. But, when we have kind of greenfield sites coming to us, we have a lot of input into the process in terms of like providing a picture of what the energy situation looks like, what's the opportunity for BESS, what's the opportunity for on-site generation, can we partner with an IPP? I mean, probably some folks are aware that in SPP right now, there's a couple of interesting developments that have happened. First of all, the generation and load interconnection queues have been merged into a single process, which actually, in retrospect, we might wonder why that didn't happen years ago. And then also, there's this new construct called HILGA, which you can quiz me later on what it actually stands for. But basically, it means that you can bring generation and load together into the process, sort of as a package. So not only is there kind of an overall study process that looks at everything kind of holistically, but you can specifically have like studied as a single project, essentially, a large load and a generator. And if you do that, you can get accelerated interconnection timeframes. And as we were talking about earlier, it's all about speed to power right now. So, we on the energy team are looking for sites like that and for partnerships like that, where we can kind of come to the table hand in hand with a developer, whether that's BESS or, traditional renewables or renewables and BESS, and kind of bring this into the study process to go a lot faster. And, we use various tools. There's the Arenias and Peaks of the world, PIQ, that help us kind of get a first pass, desktop analysis of what we think the amount of capacity is on the transmission system and where we're likely to have success getting through the process. But at the end of the day, you have to, as everybody here knows, you have to go through the study process, and that still does take some time, and there are risks involved, and real money has to be put up. So we want to make smart decisions about where we're beginning the process, so that we have a good likelihood of making it through.
Absolutely. It sounds like there's a lot of moving parts: greenfield versus brownfield, site selection, availability of interconnect. Chinmay, I want to throw this question to you. As someone who is actually designing the system and understanding what needs to be done, where is the biggest gap between what hyperscalers want? So, reliable, high quality power as the items that you mentioned, and what could be realistically engineered and commissioned today?
Yeah, no, that's an interesting question because everyone kind of like knows the narrative, like fast, reliable, unlimited power, like seems like that's the theme. But as like Sam just mentioned, a lot of constraints on the grid side. You can't really get the grid connection quick enough to get started with those projects. And I think the fundamental gap is there is a mismatch between like the hyperscaler infrastructure deployment cycle, which could be, I mean, they can build these data centers in like 12 to 18 months kind of like time frame, and then the infrastructure that they depend on to essentially operate that takes like much longer to get commissioned and like get going. So like that's grid connection, actually designing the entire power generation system, even if it's just behind the meter, right? So like there is a fundamental mismatch there. And I think like realistically, what can happen right now is creating those bridge power solutions where there is a plan to connect to the grid at certain point, but at this point, just working with that particular area's permitting process based on that, like which OEMs you can go with, and create a firm power solution based on either renewables or conventional generation sources paired optimally with like battery energy storage. I think like that's the realistic uh, and what we can engineer right now, but definitely not at the speed that the hyperscalers want in most scenarios.
That makes a lot of sense. Um, and I want to ask a question for follow-up to Tiffany, especially with the intersection of BESS and speed to power and getting these data centers up. How does the gas turbine shortage, and if you would like to explain a little bit further about what that is, into the 2030s impact your forecasts on best use cases, and which ones grow the fastest?
Yeah, for context, essentially a lot of data centers are looking to behind the meter on-site solutions to meet their power needs. And gas generation is kind of coalescing to be the centerpiece for a lot of these data centers as a solution. But the problem obviously emerges that currently there is a shortage or at least a time lag between when um, these data centers can actually get gas generation. I've heard out to the early 2030s even before anyone can get their hands on some gas generation. So obviously, as one of the use cases is best helping to optimize gas. But if, these data centers aren't able to get gas by the early 2030s, um, the main use case that we expect to see best play for data centers will again be that speed to power or flexibility argument. Just basically like, if we can interconnect faster, we're happy to install a BESS to basically reduce our peak load and increase flexibility for the grid.
Absolutely. Um, It sounds like we're putting more and more responsibility on Bess as this story evolves. My next question will be to Katherine, as a resident battery expert on this panel. From a battery technology standpoint, what is genuinely new about these AI data centers and their demands, and what is just simply repackaging what we have in functions of UPS, BESS, and grid storage use cases?
Yeah, I would say for the traditional data centers, the use is pretty simple. People just put some like lead acid batteries as a UPS, and very few of them have BBU backup units on the rack, very few using BESS. But now, if you look at NVIDIA white paper, how the future data center evolved from right now Gen 1, Gen 2, Gen 3, Gen 4, and then the Gen 4, especially the 800 volt high voltage DC architecture, you will see that the centralized UPS will be removed. And then you will see like more backup units near the compute rack. And then you move all the UPS function back to the back to the BESS. And then so this unlocks many opportunities for requirement for the new battery chemistries. For example, even at the BBU level, you have also CDUs. Mostly you need capacitors, supercaps for those like less than 0.1 second runtime power filtering, and then you also have requirement for those like synchronous compute load, which is like 1 to 60-second runtime. I'm seeing some new chemistries like niobium-based anode compared with LFP, so much better fit. I already see customers kind of replacing super caps or ultra cap capacitors with those niobium-based batteries. And also for the like 1 to 10 minutes, like kind of traditional UPS functions, you're also seeing like there's a lot of replacement of traditional lead acid with some like new battery chemistries like sodium. And also for longer duration, 0.5 to 4 hour or even longer duration, we're seeing more and more variations providing LFP, sodium on long duration flow batteries. So this is unlocking a lot of a wide range of different chemistries to fit into different needs for data centers, especially for the future data centers for like this kind of a giant AI compute campus and also co-locations and also traditional enterprise cloud and also edge AI data centers. So different data centers, they all have very different topologies. They all have very different architecture design that they need different type of battery support. So I think this is actually a really good time for battery players to really think about what market do you want to conquer, what is the best technology market fit, because you cannot like everyone use the EV battery, the old NMC batteries and lead acid to serve data centers. Right now, there's so much more new demand and unsolved problem from data center customers.
Absolutely. And it's really interesting to hear you bring up the concept of timescale and the use cases for different solutions. We have a lot of battery people on this call, and people are familiar with the concept of the different sorts of impedances of a battery electrochemical systems. There's ohmic, overpotential, and also diffusion. And so you mentioned niobium batteries that has a very high diffusion coefficient and also low surface overpotential. So I'd be really interested to hear what people have comments on for these sorts of battery performance and tracking that to the use cases for these data centers. The story today really is about deployment of LFP and BESS, and that's one of the largest reasons for a lot of the imports of BESS and safe harboring before the end of 2025. But I want to think about the other opportunities for other chemistries and such. So Katherine, you touched on a little bit in your answer just now, but what applications are most likely to create an opening for non-LFP technologies?
So for non-LFP, we're seeing, especially, so a lot of my learnings are from startups and then the company that we invested. For example, for one company that we invested called Peak Energy, they're working on sodium-ion battery technology. So what I learned, what like impressed me the most, that's something that surprised me, is for many of these compute load coupled energy. So basically the previous battery, the function is basically 99% time being idle. You just sit there waiting for like a brownout event, and then you discharge for a while to bridge the gas turbine, the diesel generator. But right now, especially for the AI compute load, where you have this kind of you need to have the energy storage piece to ramp up together with the GPU ramp up, ramp down. So you need this kind of compute coupled energy storage. So this requires very different mechanism of like microcharge discharge in a very short time. And then in this scenarios, what we find out is actually some chemistry like peak energy NFPP, they actually perform so much better. They have much less voltage polarization compared with LFP, so that they can survive much longer time. Well, LFP will probably decay in 2 to 3 years, but peak energies NFPP can last longer time. Of course, this is just on the BBU level, and then the biggest advantage of the sodium is more on the BESS, on the which they have a lot of advantage over LFP on the safety, on the lifetime, on the total cost of ownership. Because when you talk to the customers, it's not just they're paying the capex, they're also thinking about what is the maintenance, what is the safety, what is overall project meaning for the customer. So we're seeing a lot of different non-LFP chemistries getting to the market and then securing a lot of very meaningful attractions. Michael, I think you are muted.
Thank you. Yes, there's also that announcement recently with GM and Peak, and really touting the high temperature performance of sodium ion. And this is actually another issue that Jeff Don had mentioned in IBSE. He was describing to the people who attended, high temperature LFP for performance is poor, and this is something that all of the battery industry should be looking at and trying to work on. It is one of the most consequential improvements of battery technology that we have currently. I want to switch gears a little bit and bring the question back to Sam. So we've talked about some applications of battery-specific chemistries, but I want to talk about use cases a little bit more. When you compare on-site behind-the-meter storage, distribution grid storage, and transmission-connected storage, how do the value propositions differ for a hyperscaler data center developer?
Yeah, it's a great question, and I think all are important, and it probably depends on the particular circumstances of the data center in question and what each of these may unlock. Just maybe starting on the first one, behind the meter, to even have it behind the meter, you need to have space for it. And that can sometimes be challenging because, viewed by our commercial team, the one that's actually selling this product to the hyperscaler, to them, the most valuable usage of any acreage on the site is for compute acreage, not for anything else acreage. And so it can be a little bit of an uphill battle to kind of make that argument that we ought to be dedicating, a certain amount of land to this kind of different use case that's not revenue generating or not kind of directly revenue generating. That being said, if it can unlock something for us, then the value, proposition case can be made. And so, for example, with flexible data center rules, possibly coming into effect, depending on how these different regulatory proceedings go. And I think, by the way, that's probably going to be inevitable in the long run, but, which RTO goes first, and all that this kind of remains to be seen. But there, if you can have X% of your load be kind of taken off the grid kind of on demand for a period of time, then that may allow you to vastly accelerate your interconnection timeline, say. And really, I think from the utility and RTO's perspective, that's viewed as sort of a bridging solution, because ultimately the goal is to have, 100% of your needs being able to get supplied by the grid. But if it takes 3 years or 5 years or 7 years to do that, then, having this on site to allow yourself to kind of take part of your load offline, or even all of your load offline for a period of time, can be helpful. For distribution grid or level BESS, this is really interesting. I think to me is a newer construct that we're just starting to see, and I think people probably saw the Google announcement in Minnesota with Excel, where they, as part of the package, are funding the series of distribution grid level batteries kind of scattered across the grid as a way to kind of, in a way, it's a little bit like a VPP to unlock some additional capacity that the utility can then use to serve the data center. And I think this is really interesting because maybe out of all of it, it has the most kind of direct relevance to the residential consumers, who are the ones that, I guess most need to be convinced that this data center is a good idea to even allow it to get built. And maybe I'm stretching a little bit here, because I think for the average residential customer of a utility, they don't really think about the difference between the distribution grid and the transmission grid and all that. But at the same time, I think there's multiple advantages of kind of scattering these systems across the grid, because it increases the resiliency and therefore, ultimately the uptime for all the residential customers, while it unlocks capacity that can then be used to serve the data center. So I think that it's, if we can find a way to succinctly explain that to the average residential customer, then I think that can be sort of like, because we get asked, well, what's in it for me? Why is this data center good for me? And once you get past the, it's going to use up all my water, which it's not, and it's going to increase my electricity bills, which it shouldn't, especially in places that have large load tariffs that have all these protections. We still need to be able to say something about, well, what is it doing for you? And so if we say, well, we're actually hardening the entire distribution grid, which your house is actually part of, and it's going to make your power more reliable while it's also, putting downward pressure on rate increases. That's, maybe a case that can be made to kind of unlock some of that public perception stuff, in addition to allowing the data center to come online faster. And then finally, transmission level, obviously those projects tend to be bigger. And so just first and foremost, that's probably the most important thing about them, because we can get more capacity, out of it to be able to serve the data center with. And there's also economies of scale. Of course, the larger you get, it pushes the cost down, or the per unit cost down, which is helpful. But it can also take longer to build in some cases. So there are trade-offs. But I think all can be valuable. And frankly, we're looking at all of these options at all of our sites, because we're just trying to get as much capacity to serve the data center as we can, as fast as we can. And we need to consider all the options and kind of run the calculations on the value proposition for each in all cases.
I like the perspective. And discussing value proposition, I want to re-examine this on a little different lens. And this question's for Chinmay. In your experience with risk appetite of hyperscalers and data center builders who are integrating new battery technology into greenfield projects, who tends to lean more conservative, and who is willing to stomach more risk? There's like these safe options, like LFP proven technologies, and there's this new exciting but also maybe unproven technologies. Who's willing to stomach that risk?
Yeah, I mean, I would say, like, from what we are seeing, the risk appetite is low in general, where that's the hyperscaler or the data center builder, and I think, like, for the right reasons, for the operational, like, data center project. What we are seeing, though, like, there's like definite effort on, like, testing out different technologies on the generation front, on the energy storage front, but in a pilot form factor, where they're trying to test out, like, different combinations, testing out different edge cases, connecting, like, either smaller GPU loads or representative loads to figure out, like, how the entire integrated system would work out. And then essentially get that proven solution to gigascale campuses. So yeah, I think risk appetite, I would say, again, low in general, but definitely a lot of interest in verifying the new technology and making sure that it works at a larger scale.
Absolutely. The urgency and the need is driving creative solutions, but really the critical load applications are still using the tried and true sources of power and energy storage. Just as a last follow-up before we get to our closing question, Katherine, you work with a lot of startups. How should startups prove bankability fast enough for these really fast and data center timelines? We're seeing the next 2-3 years really is that key build-out time.
Yeah, I would say from 2 points. One is it's literally kind of not that feasible for a new chemistry to get into like already mass production to feed, let's say, Q4 2026 or Q1 2027, the demand or the requirement from the customer. So I would recommend battery startups to really look for the future architecture design, because right now also, like, when I visited the Switch, one of the largest co-location, from now to 2028, they already have all the architecture design, all the suppliers source. What they're more interested in is beyond 2028. What are the new kind of architecture and equipment needed for them to design a future data center? So I think it's very important to engage customers early on, know what is exactly their design roadmap moving forward, that you design your own kind of like your own manufacturing scaling up plan. And also I would also like this is another learning from our portfolio companies. I would recommend startups to not only battle on your own, but also to partnering and leverage all the great forces in the market. For example, we see like Ford is right now shifting to ESS, GM shifting to ESS. So some of these big companies who can endorse your technology, who can help you with the supply chain. These are all, and also there's a lot of like data center and traditional like power energy companies. They are looking for new solutions. So partnering, and also hyperscalers as well. They are deep pocket. They have they have like $billion just set aside to invest in new technology. So partner with someone else, like partner with someone who can provide you capital, endorsement, and then customer relationship to accelerate your bankability path. I think this will be more practical for startups to plan ahead and also engage ahead.
Absolutely. Thank you for that answer. We have a couple of minutes left. I want to ask one closing question to all of our panelists before opening it up to the floor for folks to ask questions. If you have a question in the audience, please do raise your hand after we get to that part of the panel. So my closing question for all of our panelists, for a battery company listening today, what is one capability it should build or strengthen if it wants to serve AI data centers credibly? And I'll start with Tiffany on this one, and I'll work down the line.
I think the questions that we get the most often in terms of use case is at this moment, it's gas optimization for BESS and how BESS can play a role in basically optimizing gas generation sizing and operations. I do think that just based on the current pipeline of what's likely to get built, it's not going to be maybe some of these other sources like nuclear, coal, or maybe some of these like more ambitious new ways of powering data centers. So I think being able to really optimize how your BESS performs with gas would be what I would focus on.
It's a very balanced answer. Thank you. Sam?
I think I would say kind of proving your path to scalability. And there's probably multiple ways to do that, but ultimately, if we're looking at new technology, there's a pretty high barrier to entry, as we were kind of discussing earlier, because we're serving our hyperscale tenants ultimately, and they have very strict requirements as to what they need. But we have to know that it's reliable, and we have to know that it can scale to the size of data center that we're building. So showing that there is some kind of track record, having enough years or whatever, however much time frame worth of data, and then understanding what the kind of manufacturing plan is and scale up plan is, how the supply chain is going to work, how we know that you're going to be able to secure all that, at what cost, are all kind of important questions that we would look at.
Perfect. Thank you. And Chinmay?
Yeah, I would say like from the operational standpoint for all the like battery players is very important to integrate with like all the leading EMS providers. Essentially EMS acting as like that spine for the larger like data center infrastructure. We are noticing that it's like increasingly important for that battery and EMS system to integrate well. And there could be like a lot of issues when you actually get to like factory acceptance testing. So if you have like some efforts already done on that front where you're working with a EMS provider and you have like set libraries for different primary generations and like how that would integrate with your battery energy storage system, I think like that can surely help speed to market, speed to power scenarios as well. So I think EMS integration, working with EMS is like one big thing to focus on.
It makes a lot of sense coming from your background. Thank you. And then Katherine, please close us out.
Yeah, I think I'll just same answer as Chinmay. So because batteries were a component, what customer want is not a component; they want a solution. So what is solution is like, here's better. So you have to work with EMS companies, you have to work with integrators, you have to work with PCS, you have to work with different, you have to think about how you integrate with SSC if you think about the future architecture. So you're not providing a component, but you have to embed your component into a solution. So this is the key where really the partnership and understanding who you should work together with is very critical.
Absolutely. Thank you. Thank you, everybody, for your time here. This is a really fantastic panel.